All right, good morning, everybody, and welcome to the EPA's Computational Toxicology Communities of Practice. My name is Cameron Clark. I'm a student contractor here at NCCT. And today we'll be hearing from Ann Richard, a research chemist at NCCT, and her presentation is entitled Characterization and Exploration of the ToxCast High-Throughput Screening Chemical Landscape Using Modern Cheminformatics Approaches. Before we get started, I wanted to ask if there are any updates. Are there any Tox 21 updates? Any NTP updates? NCATs? FDA? ToxCast? Or ExpoCast? Alrighty, hearing none, I'm going to go ahead and let Ann take over, so I'm going to queue up her slides here. If you don't mind muting your lines, that will make things easier for us, and if you do have any issues with audio or video, please speak up either on the phone line or in the chat box on Adobe Connect. Lovely. PowerPoint is being difficult, but hopefully it'll get.
It's probably a big file.
No, it's okay. Here we go. All right, hopefully everybody can see that okay.
Morning, everyone. My title is actually, I forgot I had changed it for the announcement, but similar content. I want to try to, sorry, Cameron, how do I move this forward?
If you just use the arrows, it should work. It's being a little slow to respond, is it not?
Yes, it is. While Cameron's doing that, what I'm hoping to do today is to walk you through
Sorry, you're not recording.
no. Stopwatch. Sorry. What I'm hoping to do today is to walk you through a paper that was published this summer that attempts to go back over the 10-year history at this point of constructing the ToxCast library, and to begin to think about how to apply what we know and what we can do with the chemistry and the cheminformatics analysis of the library to help us to achieve the goals of the ToxCast program. As soon as Cameron gets to the first slide, the paper is online. It was published in August on Chemical Research and Toxicology. It is open source, openly available, so it can be downloaded. I would just refer anyone who wants more details about anything that I'll be talking about today to refer to the paper for references. We have supplemental files that include structure files and data files that were used to generate many of the figures.
I mean, we can do this. Is this okay?
Yeah,
rather than
totally
seeing that?
fine.
All right, then that's
Totally
fine. We'll just do that.
Okay. Okay.
Let me try, because this is what they're seeing right now. This is why we try and duplicate, but it's a large file, and it seems to be grumpy with us. All right, let's see. Okay.
Oh, there we go.
So it should be responding. It's just being a little slow.
Okay. So here is just the reference to the paper. It was featured on the cover of the journal for the month. And let me just launch into the talk, if I can get it to move again. Sorry, Cameron. We've got some, maybe some big graphics are slowing things down. I would also just add that most of what has been published thus far, and perhaps this community has heard about the ToxCast program, has really dealt with the biological testing aspects of the program, with very little sort of consideration of the details of the actual chemical library, other than it's big. So this is taking a different tact. So let me just launch into what the purpose of this library was. To state, we are trying to probe the chemical-biological interaction activity space that's potentially relevant to a broad spectrum of toxicological outcomes of regulatory concern. It's a lot of verbiage, but basically we don't know about a lot of the activities of much of chemical space. ToxCast was launched to try to generate high-throughput screening data to be used for developing predictive models to support testing prioritization and risk assessment. The history, the organization of this talk and the paper was in three parts. One is looking backwards over the history of the library construction, asking questions, addressing the questions, what were the main drivers and inputs to our selection of the chemicals? How did the library expand in phases over time? To what extent is our library limited by practical constraints? Not only what could we buy, what is testable, but in chemistry space, can we begin to define what the boundaries of the library are? And finally, what are quality concerns and how are they being addressed? Because this speaks directly to the integrity of the entire program. Do we know what we're actually testing? The second part of this is, okay, we've built the library, now let's ask what's in it. We have chemical identifiers that have been collected, the standard chemical names and CAS numbers that we all know and love. But this is a physical library. These are physical samples that have been procured primarily from commercial suppliers. We have thousands and thousands of bottles, solutions, platings, and so forth to track and to characterize. And finally, we want to move all of this into the structural realm to give us the power of being able to generalize based on structural features and to be able to predict into the uncharted chemical space. Thirdly, and perhaps most importantly, we've built this library over many years. We can now say what's in the library. Now what we want to do is to ask, what is the library doing what we want it to do for us? Does it provide sufficient coverage of chemicals of interest? Is it sufficiently diverse to span the range of toxicity mechanisms and outcomes of concern, many of which we may not even know at this point? And does the library provide sufficient coverage within local regions of chemistry space? And by this I mean chemical classes of concern to enable local model development. I'm highlighting here in red the terms coverage and diversity because we cannot really examine these characteristics or metrics unless we have some relative space to compare them to. Also, this term sufficient is also very relative to the questions we're asking. They may be sufficient for some purposes and not for others. So what we really have to try to do to answer this question as best we can is to consider, does our ToxCast library satisfy coverage, diversity, and toxicity mechanisms concerns relative to the chemicals we're interested in, relative to EPA's target inventories of environmental, industrial exposure chemicals and chemicals of greatest concern. So moving on, moving backwards to the history of the program, most of you are probably familiar with testing phases 1 and 2. What I tried to do with this paper and moving forward is to really clarify some of the nomenclature so that we're all talking about the same thing. I have used Roman numerals 1 and 2 to refer to the temporal phases of the program. The earliest testing phase was completed in, I believe, 2011. Testing phase 2 data was released at the end of 2013, I believe. The second column in the table at the top refers to the chemical subsets that were tested and screened within those larger testing phases. And there we can begin to define exact numbers of chemicals that were tested, and I have defined these in a way that they are exclusive and non-overlapping within the testing phase. So this is through ToxCast Phase 2. The other thing I wanted to underscore with this figure is that through to the end of testing Phase 2, we contemporaneously built the Tox21 library, which is much larger. That Tox21 library is in turn feeding much of the Phase 3, I'm sorry, I'll show that in a moment, the Phase 3 testing currently underway. So, and the bottom figure just attempts to show, again, the idea that we are covering assay space and chemical space in different depths. So Phase 1 and Phase 2, we had approximately 1,000 chemicals with full coverage of our ToxCast assay platforms. Tox21, in turn, is a much smaller assay coverage, but a much larger chemical coverage. So expanding, I want to go back to the process of how we expanded Phase 2 because that was the largest expansion of ToxCast library to date. The reason being that we were also building Tox21 library at the time. And to give you an idea of the numbers of chemicals, we brought in hundreds, literally hundreds of CAS listings, primarily from Actor at the time, to nominate chemicals for procurement for inclusion in these libraries. The first step, we had about, I believe, if you look at the bottom of the figure, the x-axis, we had about 19,000 chemicals that were originally considered. We eliminated with just gross filters things that we believed based on computed properties and what we knew about the names and CAS numbers. We excluded a lot of metals, mixtures, and used some gross filters to remove extreme chemicals. That gave us a list of about 7,000 chemicals that were candidates for procurement. Those went out to a contractor, many of which we were unable to procure or were cost prohibitive. So that brought us down to about 4,000 chemicals, 4,400 chemicals that we actually did procure and that became part of our physical library. Of those, about 8% were insoluble in DMSO or were volatile, deemed volatile. That became our Tox21 library of about 4,000 chemicals. Then we further prioritized for cost and practical reasons to add chemicals to our Phase 2 program, and then a little bit later to screen an additional 800 or so chemicals in a subset of endocrine assays. So that just gives you kind of the overview of how we got to the Phase 2 library and the Tox21 library. There was a tremendous amount of stakeholder and EPA inputs. And again, we were exclusively basing this on CAS lists, no chemical structure considerations at this point. So where are we now? Yes.
On the last slide.
Yes.
So we have a high throughput data and all data for all.
I will show you in a moment. Okay. So expanding into Phase 3, just to give you an update of the previous figure, we largely are taking chemicals from our Tox21 on-hand procured inventory, moving them into additional testing, trying to do it in a more strategic way, bringing on new assay platforms for the ToxCast program, as I'm sure you've heard about in other talks. And procuring smaller numbers of chemicals to meet additional programmatic needs. And these could include things like flame retardants and reference chemicals and other types of chemicals. And again, we're trying to add depth into the assay side of the program as well as on the chemical side, while maintaining almost complete coverage and overlap with our Tox21 program. So this slide is intended to give you kind of a snapshot. I pulled these data, or someone pulled it for me, in January of this year. And this just gives you sort of a snapshot of the assay coverage per chemical, as was just asked about. I've also tried to represent on this figure, which is a bit dense, I realize, the temporal expansion in going from left to right as we've added inventories. The bottom blue bar indicates the Tox21 chemical assays. You can see from this figure as well that we have most of our assay coverage is up through the phase 1 and phase 2 inventories that were part of the phase Roman numeral 2 testing phase, less coverage in the E1K, and beginning to have increasing coverage in phase 3 and E1K now, but not necessarily showing up in this figure. So this is kind of a reality check in a sense. It's also giving you a sense that for some chemicals we have a lot of assay coverage, for some chemicals we don't. Sometimes this is influenced by what chemicals were testable, available at the time, the plates were submitted to the contractor, and so forth. And some chemicals we've run out of and could not reprocure. So there's a lot of practical considerations here. But most of all, I think the practical consideration is to represent with this figure that we have a physical library. This is not just theoretical chemistry. This is actual bottles, samples, and chemicals. And what becomes really important at this point for the integrity of the program is the quality concerns about, do we know what we're testing, what's in the bottle, and how do we go about making sure and building that quality underpinning to the entire program. So this slide is intended to give you an idea of all of the work that really underpins the program. At the bottom, we have our laboratory management system, basically. We've built an in-house system called ChemTrack that tracks every single bottle, solution, plating, shipment, vendor that we have ever shipped with this program. We have analytical chemistry through the Tox 21 program for the majority of our chemicals, not necessarily for all the different supplier bottles. And so all of that has been tracked. In the course of collecting these data, reviewing data that comes from suppliers, including the certificates of analysis and MSDSs, we have learned where we need to be more careful in our curation, where we are seeing errors, where we feel we need to apply more stringent review process. And that has informed, in turn, our chemistry curation, which is through the DSS Tox program, which some of you may be familiar with, which moves our physical library information into the chemical structure domain. And we have a lot of capabilities as well in that domain to bring to the problem. But I would just point out here in the yellow bubble, these are some numbers to give you an indication for the kind and the scope of the problems that we see in the supplier-provided information. 5% of the chemicals that we have procured are missing a CAS or a name. That we just have a catalog number and we have perhaps a certificate of analysis. 1% are missing both. We have only a structure that was provided. The count type of CAS name conflicts, where the CAS and the name don't agree with what we believe and what we have confirmed from our sources from suppliers, have a similar frequency to public lists, which is quite substantial. It's about 10 to 15% typically. 22% of the supplier structures conflicted with the ultimate DSS Tox structure that was assigned after our relatively rigorous COA and curation process. 22% of the structures that we were provided by suppliers disagreed with our final curated structure, which is why we put so much effort into our QC. 11% of these were salt hydrate discrepancies, which we kind of expected. 8% were stereo differences. So hopefully this gives you the sense that our curation that we brought to this library and to this program really is above and beyond what most high-throughput testing programs are doing, and we really feel that it's necessary and it adds to the integrity of the program. So let's now turn to, we've built the library, we've instituted all these quality checks and processes. Now we can stand back and say what's in the library, finally. And is it fit for the purpose of the ToxCast program to really feed and enable the development of predictive models? So the first thing we do is to retrospectively go backwards and say, okay, there were a whole lot of inputs that went into building the library, primarily from CAS listings. Now let's ask, did we actually achieve the kind of CAS listing coverage that we intended to achieve with building the library? So that's the first step. Secondly, we're going to take a look, once we move into the structure, physical chemistry realm, and we can compute physical chemistry properties, we can begin to look at some of the limitations of the properties or the library in terms of what data we've collected, how many, what kind of chemicals are DMSO insolubles and volatiles, and can we begin to characterize those sets of chemicals that we were not able to test that begin to define the boundaries of the library. Next, we will look at target inventories that represent what we're calling the environmental exposure landscape, and I've selected a few that we have on hand to try to begin to ask the question, does our library reflect the diversity and content of these libraries that we're interested in trying to predict for? And finally, what do we think we know about structure relationships with toxicity and metabolism? And of that knowledge base that has been collected in commercial and public tools, things like structural alerts and models, how much coverage do we have in our library of these knowledge elements, and is that going to be helpful moving forward? So step one, what's in the library? This is simply an inventory of our actual chemical listing once we have mapped our bottle solutions and gone through the curation process. We have 4,226 generic substances, meaning a unique CAS number and name. I should point out that CAS is specific to salt, hydrate, and stereochemistry usually. Not every chemical, including many metabolites, biodegradation products, have a CAS number. That is a limitation of using CAS. Sorry.
The leader has muted your line. To unmute your line, press #6.
Test, if it's a complex mixture, an oil, something like that, is going to have a structure. So I've just indicated in the table here the actual numbers of things that have CASs that we've been able to structure annotate. Notice that we do have some inorganics. We have some organometallics, mixtures of isomers, mixtures, formulations, and so forth. And at the bottom, you can see we also have duplicates on desalting, meaning that we have over 200 chemicals that have very slight variations in terms of their salt form, which also could be something interesting to look at in the assay space. So asking again what's in the library, if we simply look at the CAS list that is in our ToxCast inventory, and we overlap this with many other CAS lists that we have now collected in ACTR and DSS Tox, it requires exact CAS matching, which is not going to be taking into account stereo and salt forms, et cetera. And we can't, again, consider the no-CAS substances. So here's just a snapshot. I pulled out 19 inventories that are pretty representative of the kinds and maybe the exact lists that we used originally to create the library. And here you can begin to see the overlap of our ToxCast inventory and how much coverage. These percentages in red give you the percentage coverage of the entire, at the bottom, for instance, ToxRef inventory. We have 77% of ToxRef is in ToxCast. 40% of the cancer potency database is in ToxCast. Something like, okay, so where is IRIS? IRIS, 57% of IRIS chemicals are in ToxCast, and those are explicit overlaps. So we've also tried to cover a lot of these other use cases, and you can begin to see also the temporal increase in coverage as we go from phase 1 to phase 2 to phase 3, particularly in the IUR, which is the HPV and industrial chemicals. You're seeing a lot of expansion in phase 2 and phase 3 in coverage of that type of chemical space. Another view of the CAS overlaps is shown here in this nice colorful picture. And what I'm showing here is chemical by chemical, how many lists each individual chemical along the bottom axis occurs in all of these same 19 lists. And you can look at the density of colors and so forth. What I would show you, or what I would point you to, is here's phase 1 in the initial segment. We have almost complete coverage of those phase 1 chemicals were primarily pesticides, as we all know. Those are primarily data-rich pesticides that were incorporated and taken from ToxRef TB. So you can see almost full coverage in the pesticide and ToxRef, but also notice a lot of overlap with many of these other lists. The most density in this plot occurs in the phase 1, phase 2 inventories, and that was by design. That was pulling the highest priority Tox 21 procured chemicals, moving those into this higher throughput coverage of assay testing. The frequency plot at the top here shows you the higher frequency overlaps relative to later testing in the phase 3 inventory, where we're pulling in chemicals that have less and less overlap with these many lists. So this is by design. This is showing that we did try to achieve multiple overlaps. We're getting more bang for our buck. If we're testing a chemical that's on 12 lists, it's of interest to 12, many more stakeholders, and we are potentially getting more information for our dollar. So the highest frequency, again, is in these early phases. We also have the greatest in vivo data coverage by design, because in vivo data is absolutely necessary to anchor any predictive modeling efforts that we would pursue. So we can turn to asking what's not in the library. And here, we're going to be looking at DMSO insolubles and volatiles, because we actually get information back on our physical library about things that cannot be solubilized and things that end up volatilizing after we've procured them. So that is our experimental validation of these two properties. What I've done here is go backward to use, log P was used as a filter very early on in our procurements. That filter was relaxed somewhat because there were many chemicals that were very high priority, very high interest. We don't have 100% confidence in these prediction models, so many chemicals got through these filters because of the high priority concerns. But if we go back now retrospectively and look, 8% of our procured library were DMSO insoluble. If we look at those chemicals relative to the total library at the bottom, you can see that 50% of the chemicals were within the range that most of our ToxCast library falls in, whereas the other 50% are outside of that range. So you really are seeing a validation that these extreme log P values, both in the high and low ends, are much more likely to be DMSO insoluble. It's not sufficient to allow us to build a good model at this point. We also found many metals and oils and mixtures that were also more enriched in the DMSO insolubles. On the volatile side, not surprisingly, these are primarily low molecular weight compounds. Volatility and molecular weight don't always track 100%. You can put low molecular weight compounds in solution. They can be stable for testing for quite some time. So again, there's enough uncertainty to motivate us to put some of these chemicals in the library, see what happens. But on the other hand, we know that there are potential issues with volatiles in particular. We need to go back to the assay data. We need to start looking at assay profile bioactivity performance for chemicals that are suspected to be volatiles, and that could explain lack of activity. I also would make one comment here about the DMSO insolubles. We have moved forward. We've taken the 400 or so DMSO insoluble chemicals that we have on hand. We've predicted water solubility for these, and we have created a water soluble plate of about 110 chemicals that will be put into some limited testing. These include Roundup, glyphosate, I believe, and a few, several other chemicals that are of high interest that never made it into the testing library. So these kinds of considerations give us an opportunity to focus our efforts on how to expand the library and what kind of problems we need to be dealing with. So let me turn now to evaluating the coverage of our potential target inventories. So now that we have the library, we have the testing space, can we ask how relevant are our ToxCast chemicals to other inventories that are of high interest? I've used a set, I want to introduce here the ToxPrint set. It's actually 729, not 792. This is a fingerprinting method. These are chemical substructural features. It's a public set that was put out by, it was funded by FDA and is publicly available. It was designed to cover the kind of environmental and industry, commercial, drug landscape that both EPA and FDA are interested in. And it lends itself to computation, to visualization, and to sharing. So I have begun using these in a number of applications. I will use them in some of the comparisons to show you. The three inventories that I created to try to begin asking this question, how representative are ToxCast chemicals of other inventories? SERAP is a large effort that was undertaken here to screen approximately 35,000 chemicals spanning what we call the EDSP universe, the endocrine disruption screening program. And these are largely taken from the same kind of inventories that we use to inform construction of ToxCast, environmental chemicals, commercial chemicals, use chemicals, some drugs, and so forth. So that inventory is publicly available. So we use that because that is sort of a tenfold larger target inventory that we might consider ToxCast being applied to. FDA drugs, this was taken from the LeadScope program. It's publicly available. Approximately 7,000 structures were considered because it's of interest to say, you know, for many in the pharma industry who are looking to ToxCast program to inform their efforts, how relevant are our chemicals and what we can learn from ToxCast to the drug space. And finally, we have a data set of about 800 chemicals. BMD HHA was a publication put out by Vignal et al., benchmark dose human health assessments. These are the most data-rich risk assessment chemicals that we have, and so it's of interest to see how much coverage we have of that space as well. So the first thing I wanted to do was to look at the ToxPrints. ToxPrints were independently developed from ToxCast on a much larger space of chemicals, including TSCA chemicals, HPV, FDA drugs, FDA food additives, and so forth. How representative are these features of our space? It turns out about 84% of the ToxPrints are represented in our ToxCast inventory, if I don't consider the individual metal atoms, because we purposely excluded a lot of metals from ToxCast. That is, in turn, pretty good coverage. That additional 16% are going to be things like nucleic acids, some more food additive type of features, and that could be a place that we begin to look later on in terms of expanding coverage. We could also then look at how many features are present in each of the ToxCast chemicals. Why this is important is because we're intending to use ToxPrint as a fingerprinting method. A fingerprinting method is only as good as how represented it is within your library. If your chemicals don't contain any fingerprints, you're not going to have any information to bring to bear for that chemical. So we're, again, seeing quite a lot of coverage of the ToxCast inventory of this feature set, which tells me it's a good place to start. So then what we do is I'm looking here at the ToxPrints across the testing phases to give you a sense for what these things are. They're basically ways to define local chemistry, and they can do it in a relatively intuitive way, both in the names of the chemotypes on the left-hand side of the figure. You can actually begin to interpret what these are. You can see on the right-hand side, I put a few images of some of these chemotypes to show you they can represent what we begin to think of as chemical classes. These are scaffolds, they're types of bonding, they're types of alkanes, aromatic systems, they can be individual atoms. So it provides a very useful way to deconstruct the chemical space into these very well-defined local chemistry domains. What I can also see as we've expanded from phase 1, phase 2, and phase 3 is in some cases in phase 1 I didn't have any coverage of some particular chemotypes. these began to be added, and I'm enriching certain chemotype spaces as I moved from phase 2 to phase 3. This is another way to inform the expansion and to begin to build local chemistry coverage. Another thing we can do with these tox prints, because they give you an objective way, a common plane on which to compare very diverse inventories. So ToxCast contains drugs, but is not going to contain all the drugs in the FDA drugs inventory. Likewise, SARAP is 10 times larger than ToxCast, so it's going to contain many, many chemicals that ToxCast does not. We can't do a direct overlap to inform us how well we're covering that space. So what I've done here is I've scaled the two larger inventories, FDA and SARAP, to the size of ToxCast, so I can look at the relative coverage within the local chemotype domains. And again, what you can begin to see are areas where I have good coverage. It looks overall, if you stand back from this figure, they look kind of similar in terms of the chemistry space covered. But you can begin to identify these subdomains where SARAP, for instance, has many more chemicals of this feature type, for instance, the azo bond, than does ToxCast. And similarly, drugs contain a lot more of some of the pyridine and other types of features. So there's a lot that you can begin to glean, and you can begin to also drill down into some of these local domains. This next slide is showing an attempt to do that. So we could ask, from the previous slide, let's look at some of these areas where SARAP has a lot of chemicals containing a chemotype and ToxCast does not. Why is ToxCast not covering that local domain? I pulled out a few examples here of tox prints in SARAP that are not present at all in the ToxCast library. And you can begin to start seeing, well, I can look at this and I can say some of these are going to be very reactive and not procurable. There are others, the pHs are difficult to procure, many are volatile. So you can begin to start characterizing why local domain coverage is a problem or not, where we need to focus additional efforts moving forward. So I think it's a very valuable approach to trying to get a better handle on what we're actually testing. Another thing we can do is additionally look at where we have good coverage. Here I'm looking at ToxCast versus SARAP for three high-interest, well-known types of subsets, phthalates, perfluorinated compounds, alkanes, and some biphenyls. And you can see from the numbers, ToxCast has a pretty good representation of chemicals that are very well represented as in SARAP. And you could begin to start thinking of building local SAR models around these local domains. Not remembering now that in addition to just the chemistry, we have all of this high throughput testing data for chemicals within these ToxCast domains. So this becomes a very powerful approach. The next slide, I've looked additionally, in addition to local features, we've looked at global physical chemical properties to compare these inventories, just to see if we can see areas where we're biasing our ToxCast library in terms of property space. If you look at the left-hand figure, you can see that SARAP and the risk assessment data set, both are the shape, the size, the extent of the figure on the left appear somewhat similar. We do have more outlying BMD chemicals, and I have looked at these. They tend to be things like metals and organometallics and very small organics, which we know we're not covering well, but they are data-rich chemicals. On the right-hand side, if I do a comparison of ToxCast just to drug space and to the subset of donated failed pharmaceuticals, there's only 135 of those in our ToxCast library, you can actually start pulling apart and see that drug space by its very nature is designed to be more complex than many industrial commercial chemicals, and that the ToxCast chemicals tend to be less polar than the drug space. So there's interesting things that one can begin to explore. Lastly, I did a calculation here asking a little different sort of question. if we are trying to extend ToxCast into these larger target space for the purposes of prediction, it becomes relevant to say how close is the nearest neighbor chemical to each and every of the 30,000 SARP chemicals. That's what's shown in this top radial plot in terms of density. And the calculation indicates, based on just a basic Tanimoto similarity, that 75% of the SARP chemicals have a one or more ToxCast analogs that are greater than 75% similarity. I know that's a lot of words there, but hopefully you get the gist of this, that most of SARP has a close ToxCast analog. About 58% of the BMD chemicals have a close analog at that level of similarity, and about 61% of the drugs, which actually was a little surprising to me. I didn't expect that high a percentage of drugs, but I think it also speaks to the fact that we actually have a lot of drugs and drug-like chemicals in the ToxCast inventory because of their known bioactivity profiles. So turning now away from the landscape comparisons to the knowledge prediction landscape, what do we think we know about structural alerts and structural aspects of toxicity, and have we incorporated a good proportion of those in our library? I turned here to two different resources, one public, the OECD Toolbox, which contains a number of profiling methods. Grace Patlowitz assisted with this part of the project. And we also turned to the LASA knowledge base in terms of Derek and Meteor. We had a license through 2013 or 14, I can't remember. So we, at that time, evaluated about half of the ToxCast library. So the question then becomes, of these total number of alerts, how many are actually represented in our library, and how can we begin to use that knowledge to dive into our chemical assay space? So this is a representation of the Hess repeat dose toxicity alerts. What I'm showing here is on the bottom axis, the number of ToxCast chemicals that actually occur in each one of these categories that are identified by an alerting feature in the Hess repeat dose model. And you can begin to see quite a bit of representation, 20 to 60 chemicals in each one of these categories. What kind of structures are they? What kind of assay profiles are local to these known bio-alerting categories? And can we begin to use these categories to help us to amplify some of the signals in our assay space? Similarly, we use the developmental DART toxicity alerts. These were developed by Procter & Gamble. George Daston et al. Had a publication on this. And these have also been found very useful. And we also have pretty good coverage of these. And we can identify some alerting classes that have a pretty good representation within ToxCast. We have many chemicals that contain the DART alerting feature. Can we begin to go into our ToxCast assay space and see whether we can find activity patterns that are coordinated with these subspaces? I can quantify this as well in terms of the kind of figure shown here, where I'm asking, again, as I did with the tox prints, coverage in two directions. How many of the alerts are represented in ToxCast? What percentage of the alerting space does ToxCast cover? And in this case, we have 72% of Hess and 91% of the alerts in those two models are detected in ToxCast chemicals. That speaks to the coverage of the knowledge space. On the other hand, going in the other direction, we have about 47% of ToxCast chemicals contain an alerting feature, which means we've enriched and loaded our ToxCast library with as many potential toxicants as possible. Again, needed in order to develop any types of models. So hopefully you can begin to appreciate now the power of these approaches is really beginning to articulate these subdomains and quantify these types of coverage in terms of what we think we know. Moving to, lastly, to Derek, with Derek, we have sets of alerts, and we have a smaller number of sets of endpoints. Derek can be used based on recognition of structural alerts. It predicts for the endpoints. And you can look in both subspaces to look at coverage, to look at grouping chemicals according to both alerting space and endpoint space. And here again, I'm just showing the number of toxic chemicals in each one of these subcategories. These are potential candidates for further exploration within these subsets. And again, I can quantify the actual coverage of the knowledge space of Derek alerts, Derek and Meteor both, Meteor being biotransformation alerts. 80% of the alerts are detected in our ToxCast set. That's pretty good coverage of the knowledge space that Derek and Meteor, which have been around and been building for about 25 years now, and they tap the literature and their consortium of industry, government, academia. So that is kind of an independent way of assessing and characterizing what we think we know about structure relationship to activity. Similarly, at the bottom, 58% of toxic chemicals contain a Derek alert. 84% contain a Meteor biotransformation alert, meaning there's a lot of potential for biotransformation in our subspace, which is a whole other story to tell for another time. So let me now cycle back to the original slide and questions that I posed at the beginning of this talk. Does the library provide sufficient coverage? I have changed the term sufficient because that is a relative term that has to be applied to specific questions. Rather, I've used independent metrics to try to assess an extent of coverage. And I think we can say with some confidence now that we do have broad coverage of chemicals of interest based on these inventory comparisons. We have broad diversity based on a full range of, looking at alerting features, looking at the models out there, and broad coverage of local regions of chemistry that can really empower some of these modeling approaches that I think will become more and more useful. So I would answer yes, and hopefully you've been convinced as well. Again, however, everything is relative to the target inventories of concern, relative to the questions we are trying to ask, which it should be the case. Is it fit for purpose means what is our purpose? So just to leave you with a few indications of where we are currently going beyond what we've done in the past. We're trying to build on these chemotype capabilities to expand the local chemistry domains, to move into the assay space, to begin to look for enrichments of assay signals within local chemistry domains. A strategic expansion of the library as we try to focus in the biological space, and be more selective of which chemicals are being tested, mainly driven by practical financial constraints. Secondly, on the TOX21 sphere, looking at a similar sort of examination of the larger 10,000K library, 10K library, as well as really starting to look more carefully at the analytical chemistry data. We have about 15% of our compounds that have quality concerns based on analytical chemistry, and can we begin to characterize where in chemotype space those concerns are? That also is going to impact how we interpret our assay data. And finally, we've got a number of collaborations with our physical library being supplied for ExpoCast and collaborative efforts in non-targeted screening. We've supplied mixtures of our entire library. We've partnered with commercial mass spec companies, 7 of them, to generate high-res fragmentation mass spec for deposits into the public domain. So really look for a lot of information that is going to be adding to this underpinning of chemistry that I think will really start augmenting and helping to enhance the value of our ToxCast assay space. So with that, I simply thank everyone, of course, in our ToxCast program, as well as our past leaders, Bob Kavlock and David Dix, who really played a huge role in helping to get this program started and building the initial library. So with that, we have a few minutes remaining for questions.
Yeah, I want to start off seeing
The
if anybody
leader
on
has
the phone
unmuted your
line
line.
or in the room has any questions for Ann.
Everything's crystal clear,
Yeah,
right?
Nobody's speaking up, so I'm going to check out our chat box. I was a little scared to close down this PowerPoint since it was being difficult to begin with, but let's see if we have any. All right, so we have a question from Julia in the chat box. Is there information available online detailing which chemicals may have DMSO solubility and or volatility ranges that may limit high-throughput screening data interpretability?
Yes. If you look at that link I provided on the second slide, accompanying the published article is a supplemental file. I've also posted that on the DSS Tox FTP site, which you can access from the link provided. I believe I put the FTP site there as well. So I did put supporting information, which included the list of DMSO insoluble chemicals and volatiles that went into the creation of the figures that I showed you, because as you appreciate, that had not been published previously because we had not tested those chemicals. We will try in the future to be moving more and more of this kind of information, this tagged information, as well as the analytical QC information, surfacing that with the ToxCast data through our dashboards and other data releases so that it is more easily consumed and utilized by folks who are trying to analyze our data.
Any other questions on the phone line, in the chat box, in the room?
Hello, I have one.
Go ahead.
This is Judy Strickland. And I was wondering if you characterize volatility using anything other than molecular weight, for instance, specific density or Henry's law constant? We did use Henry's law constant early on. Some of the problem was getting models to do so. We have more work to do on that front in terms of trying to retrospectively look at the entirety of the library. Yes, I realize molecular weight was a very simplistic way to characterize at this point, and there are other methods that we will be using to try to better delineate the chemicals that are of potential concern in our tested space, whereas I was kind of focusing in my slide on things that we weren't able to test, as well as things that had been moved into testing. So yes, we will be looking at some of those other properties. I am aware that there are some better models for trying to estimate volatility. We also have some ongoing efforts with folks to try to test some of these chemicals in other venues and maybe in closed hoods and glove boxes and things like this. So yes.
We've got time for one or two more. Unless Ann's answered all the questions, which it seems like she has. I do want to thank her for presenting today and thank all of you for joining us. And I hope everybody has a happy holidays.
The leader has disconnected. The conference will be terminated in 5 minutes.